Now imagine that instead of having a ring, we have a disk, right? And well, a disk, this disk is completely circular, right? But we're seeing it by one extreme, and it has a radius A, and we're going to calculate the electric field at a point P once again, at a point P, and in this sense, well, what we're going to be having, for instance, once again, is there is going to be a radial distance r, and so on and so forth, right? And from the center of the disk, point P is located at a distance x. The first thing to analyze from this disk is that the disk is, for instance, having a series of rings. So if I have one ring, and then I have a ring with a higher diameter and a ring with a higher diameter, well, the disk is a series of rings. And remember that the electric field, so this is a differential of disk, which is a ring, right? Sorry, a differential of disk, and this will exert a differential of electric field. So the differential of electric field, well, it's only going to be in x due to symmetry. And remember that this is going to be k over x over the radius, and I am going to put, for instance, from here to here, a small letter r, which is the radius, square, plus x squared to the 3/2, although from here to here, well, it's radius a, right? And that's the radius of the disk times the differential of charge. So the differential of ring is the electric field of a ring, and a lot of rings will actually make up a disk. So we can actually define the superficial, right now the superficial density, and this is called sigma, of charge, as charge over area, or the differential of charge over the differential of area. And in this case, well, the area is going to be equal to PR squared, while the differential of area is going to be equal to 2P R dr. Okay, this is an implicit derivative, such that the differential of charge is going to be equal to sigma times the differential of area, which is 2P R dr, and in that sense, well, the differential of electric field is going to be equal to kx over r squared plus x squared 3/2, and dq, which is, for instance, sigma 2p r dr. Well, the electric field is going to be the integral of this, right? So this is going to be the integral of this expression, and we're going to integrate from 0 to r, since the differential we're integrating is from the differential of the radius. And, well, sorry, once again, the radius here is a, right? So from 0 to a. And this integral is simple, because we can actually extract a lot of constants, for instance, 2p sigma constants. There is also k, which is constant. There is also x, which is constant. And there is going to be an integral from 0 to a of r dr over r squared plus x squared to the 3/2. And we can actually integrate this by substitution. So we can actually state that u is going to be equal to r squared plus x squared, and the u is going to be equal to 2r dr. So we need a 2 inside the integral. So probably it's better to actually take into these 2. And then we are going to have, for instance, p sigma kx, which are constant, integral of du over u to the 3/2, and well, we do this integral and evaluate from 0 to a by changing the variable, and well, this might be very straightforward. The electric field, which is only given in x, right? It's only given in x due to symmetry, is going to be equal to 2k p sigma 1 minus x over the square root of a squared plus x squared. So this integral, this is the electric field from a disk. You can actually perform the integral by yourself or finish the integral and you will get this result.